Okay, so today we're solving AS Math paper 1-2 from the Feb-March 2023 session. Moving on to question 1. We have a line with equation y is equal to 3x minus 2k and a curve with the equation y is equal to x squared minus kx plus 2. We need to show that the line and the curve meet for all values of k. So the first thing we'll do is equate these two equations. And then we'll bring all the like terms together on one side. Now, once you have the equation in this format, we can apply b squared minus 4ac. And since the question is asking us for the values of k for which the line and the curve meet, it can either be two solutions, which is greater than 0, or one solution, which is equal to 0. B squared over here would be minus k minus 3 whole squared, minus 4 times 1 multiplied by 2 plus 2k, greater than equal to 0. This can be factorized to k minus 1 whole squared, greater than equal to 0. Now we need to prove that the line and the curve meet for all values of k. So in this bracket, whether k is negative or positive, k minus 1 whole squared would always be positive and greater than equal to 0. Moving on to question 2, we have the function x squared minus 2x plus 5, and we need to apply a sequence of transformations on this which would result in the graph of y is equal to gx. The first one being a stretch parallel to the x-axis with a scale factor of 1 over 2. The second one being a reflection in the y-axis, and the third one being a stretch parallel to the y-axis with the scale factor 3. Let's apply the stretch parallel to the x-axis. So if the scale factor is 1 over 2, this means that inside the bracket, we need to multiply x with 2 so that the value of x decreases by a factor of 1 over 2. Next, we have a reflection in the y-axis. Which means that a point on the right side would get reflected on the left side, showing a change in the x coordinate. So we'll put a negative sign inside the bracket for x. And for the last part, we have a stretch parallel to the y-axis with a scale factor of 3. So all the y values get multiplied by a factor of 3. So gx comes out to be 3 times of the y equation we have. So the equation for the function gx comes out to be 12x squared plus 12x plus 15. Okay, moving on to question number 3. We have a curve with equation y is equal to 1 over 60 times 3x plus 1 whole square. Now, a point is moving along the curve. Find the x coordinate of the point of the curve at which the x and y coordinates are increasing at the same rate. So let's find dy by dx. This would be 2. We'll multiply the power of the bracket with the coefficient. So 2 upon 60 multiplied by 3x plus 1. We subtract 1 from the power and multiply the inner differential of the bracket. Okay. Find the x coordinate of the point on the curve at which the x and y coordinates are increasing at the same rate. This means that the change in y upon change in x ratio should be is equal to 1. So dy dx 1 over 10 times 3x plus 1 should be equal to 1. Then we cross multiply to get 3x plus 1 is equal to 10. This results in x is equal to 3. The circumference around the trunk of a large tree is measured and found to be 5 meters. After 1 year, the circumference is measured again and found to be 5.02. Given that the circumference at yearly intervals performs an arithmetic progression, find the circumference 20 years after the first measurement. Okay. So in the first part, the circumference is following an arithmetic progression. So since we need the term 20 years after the first measurement, let's take the first term as 5.02 instead of 5. We'll take the difference as 5.02 minus 5, which is 0.02. And we're finding the 20th term in this sequence. The formula for the sequence would be a plus n minus 1 multiplied by d. In this case, a is 5.02 plus 20 minus 1 multiplied by 0.02. The answer comes out to be 5.40 for the term 20 years after the first measurement. In part B, The same experiment is now following a geometric progression. So the term formula for GP is first term multiplied by the ratio power n minus 1. A over here would be 5.02. And the ratio can be calculated by T2 upon T1 in this case. Which comes out to be 1.004. Now we need to find the term 20 years after the first measurement. So again, we'll take A as 5.02 in this. So T20 comes out to be 5.02 multiplied by 1.004 power 19. The value comes out to be 5.415, so we can round it off to 3 significant figures. And this comes out to be 5.42. In question 5, we have points A and B, which lie on a circle with center C. So the equation of this circle can be formed: x plus 2 whole square plus y minus 5 whole square is equal to r square, which is unknown right now. The line AB has the equation y is equal to minus 2x plus 26. Let's suppose that this is our circle with the center minus 2 and 5. The points A and B, let's assume they lie in these 2 points. If I equate this equation with the equation of the circle, I should be able to find the coordinate B, right? But for that, I'll need to find the radius of the circle. Now, since the coordinate A is on the circumference of the circle, the length of A from the center would give me the radius. So to find radius over here, I can find the length between these 2 coordinates. Plus 12 minus 5 whole square. R square comes out to be 130. So the square of the radius in this case is 130. Now the equation of the circle I have is x plus 2 whole square plus y minus 5 whole square is equal to 130. And when I substitute this equation in place of y over here, I can find the 2 intersection points of the circle with this line, which would result in the coordinates for A and B. minus 2x plus 26 minus 5 whole square is equal to 130. We'll simplify this equation, giving us 5x squared minus 80x plus 315 is equal to 0. This can be simplified to 5 bracket x minus 9 and x minus 7 is equal to 0. The x coordinates come out to be 7 and 9. We know that 7 is already the x coordinate for A, so 9 would be the x coordinate for B. Now we'll use the equation for y for AB to find the y coordinate of B. The coordinates for B are 9, 8. In question 6, we have the expansion for x over a plus a over x squared whole power 7. We're given that the coefficient of x power 4 and the coefficient of x have a ratio of 3. Now, firstly, we'll need to find the values of r. That would result in the terms x power 4 and x. So we'll use the general NCR formula for the term. In this case, this comes out to be x over a power 7 minus r and a over x squared power r. Now the value of a over here is a constant, and in this step for now, I'll be ignoring the constants and any coefficients, and we'll just be dealing with the variables. X power 7 minus r, and I bring this x squared in the numerator, so the power becomes x power minus 2 multiplied by the power r. This can be simplified when we add the powers, so 7 minus 3r and I need the value of r for x power 4 and x power 1. So I'll equate this to x power 4 and I'll equate this to x power 1. Now when we equate the powers with each other, 7 minus 3r is equal to 4 and 7 minus 3r is equal to 1. R comes out to be 1 in this case, and R comes out to be 2 in this case. We'll find the values of NC1 and NC2. So x power 4 upon x cubed can be found by 7c1 x upon a power 6 and a upon x squared power 1 divided by 7c2 x over a power 5 and a over x squared power 2, and this should be equal to 3. Seven C1 would give me 7, and the numerator simplifies to 7a upon a power 6 7c2 is 21. Now, since this ratio was for the coefficients, I've ignored the variables x power 4 and x power 1 over here, and we'll just deal in the coefficients and equate them to 3. When I solve this, I'll get 7 upon a power 5 divided by 21 upon a power cube is equal to 3. Okay, now we have 7 upon a power 5 divided by 21 upon a power cube is equal to 3. This can be simplified when we reciprocate this. We can convert the sign into multiplication. 7 upon a5 multiplied by a cube upon 3, upon 21, sorry. So this simplifies to 1 upon 3a square after cancellation is equal to 3. I'll shift this a square to the other side by cross multiplication. So a square is equal to 1 over 9. A is equal to plus minus 1 over 3 when I apply square root on both sides. Now the question here said find the possible values of the constant a. So we won't reject either of these two values, and this would be our final answer. Moving on to question 7. We need to form a quadratic equation in terms of cos theta to solve the equation. So we can replace tan theta by the substitution of the ratio sin theta upon cos theta multiplied by sin theta is equal to 1. We can multiply the numerators and shift cos theta to the other side by cross multiplication. Now, since we need the whole equation in terms of cos theta, I'll apply the identity over here for sin square theta, which would be 1 minus cos square theta is equal to cos theta. Now, bringing all the terms on one side, I'll have cos square theta plus cos theta minus 1 is equal to 0. The values for cos theta now in this case would be minus 1 plus minus root 5 over 2 when we apply the quadratic formula on this equation. Now, the second value would result in no solutions because the least value that cos theta can have is minus 1. So this would result in no solution. And we'll solve this one. So to find the basic angle, we'll apply cos inverse on this value, giving us 51.8 degrees. Now, since cos is positive, the quadrants we'll use would be A, S, T, C, the first and the fourth quadrant. The values of theta in this case would be theta is equal to 51.8 and 360 minus 51.8 for the fourth quadrant. So the final answer comes out to be 51.8 and 308.2. Okay, moving on to part B, we need to prove this identity. So we have tan theta over sin theta minus sin theta over tan theta. We can express tan theta as sin over cos. So this can be written as and we can do the same thing over here. These two sin thetas cancel out each other. So I'm left with 1 over cos theta over here minus sin theta and sin theta cancel out. So I have 1 over cos theta. This can result in cos theta. So I have 1 over cos theta minus cos theta. Now when I take the LCM for these two, I'll get 1 minus cos square theta over cos theta. And 1 minus cos square theta can be expressed as sin square theta over cos theta. Now I need to prove that this is equal to tan theta and sin theta. So if I break the sine square into sine theta and sine theta, this can result in tan theta, sine theta. Okay, moving on to question number 8. We have a right angle triangle BCD where B is the right angle. We're given the length 4 centimeters for BC, 3 centimeters for BD, and 5 centimeters for AD. Now the sector DAC is part of a circle with center D. So if this is the center, then 5 centimeters is the radius R, and CD would also be the radius. R is equal to 5 centimeters. Now we need to find the perimeter of the shaded region, which means that we need to find the length of AC, the arc, and the straight line AC. Now for these two, I'll need this angle of ADC. And to find ADC, I'll need the angle BDC. So let's label this as X. So tan X in this case for the triangle BCD would give me 4 upon 3. And X would come out to be 0.927. Angle ADC comes out to be pi minus 0.927. Now to find the length, the straight line length AC, I can apply cosine rule using the sides 5 centimeter and 5 centimeter and the angle between these two sides. So C square over here would be the side AC. The first side being 5 squared and the second side also being 5 squared minus 2 times 5, 5 and cos of the angle pi minus 0.927. Now I'm not using the numerical value and instead using the exact value over here to avoid any accuracy error in the final answer. The length of AC comes out to be 8.944. Now we need to find the arc length for the curve AC. The arc length would be S is equal to radius times the angle, which in this case would be 5 multiplied by pi minus 0.927. This comes out to be 11.07 centimeters. The perimeter would be 8.944 plus 11.07, resulting in 20 centimeters. Now we need to find the area of the shaded region over here. We can find this region by subtracting the area of this triangle ADC from the area of this sector ADC. The formula for the area of sector is half times r squared theta, and the area for a non-right angle triangle is half times AB and sine theta. The radius is 5 squared, and the value of theta is pi minus 0.927. And the two sides of the triangle are also 5 and 5. We'll use the same angle. Area comes out to be 17.7 centimeters square. Moving on to question 9. Now we can see that the turning point can be found as 0, 2, and the domain that we're given, the turning point doesn't lie in the given domain over here. And since the function is a maximum curve, Now suppose that the x is equal to -1 coordinate is over here. All the points of x less than -1 would be below this point. So f of -1 gives us -1. And since this is the highest point in the given domain, the range would be fx less than equal to -1. Now we need to find the expression for the f inverse in this case. So y is equal to minus 3x squared plus 2. We need to make x the subject over here. This comes out to be 2 minus y. We apply the square root on both sides to remove the square from x. Now we'll change the symbols. This becomes f inverse of x Now, since we're finding the expression for f inverse for the given domain, which is less than the turning point, we'll use the negative sign over here outside the expression. So f inverse comes out to be negative 2 minus x over 3. In part C, we have the function g as minus x squared minus 1. We need to solve the equation f gx minus g f x plus 8. Okay. So let's write fx over here as well. F g x means that we're plugging in the function of g in place of x in the function f. So minus 3 bracket minus 1 whole squared plus 2. And at the same time, let's find g of x as well. G of x means that we're plugging in the function, we're plugging the function fx inside the function gx. So minus 3x squared plus 2 whole squared plus 2, sorry, minus 1. Okay, let's simplify these two. So we have the expression for f gx over here. And we can simplify this side as well to get g of x. Now we need to add f gx, subtract g of x, and add 8 and equate it to 0. And then we subtract g of x. So I'll just switch the signs. Plus 9x4 minus 12x squared plus 5. And then we have plus 8 is equal to 0. This simplifies to 6x power 4 minus 18x squared plus 12 is equal to 0. We can take 6 common from this expression, giving us x power 4 minus 3x squared plus 2 is equal to 0. And then in the middle term break this, we can get 6 times x power 4 Now we can find the values of x. X squared minus 1 is equated to 0, and x squared minus 2 is equated to 0. X comes out to be plus minus 1 in this case, and x over here comes out to be plus minus of under root 2 in this case. Now, since the question specified that the function g is defined for x less than equal to minus 1, we'll reject the positive values in this case, and we'll only have the solutions of x is equal to minus 1 and minus root 2. Okay, let's continue with question 10. We're given that at the point 4 minus 1 on a curve, the gradient of the curve is minus 3 over 2. We're given that dy dx is equal to x power minus half plus k, where k is a constant. We need to show that the value for k is equal to minus 2. Now, since we're given the gradient of the curve, this can be used as a value for dy dx. And we also have the x coordinate 4, so we can just plug it in this equation to find the value of k. So minus 3 over 2 is equal to 4 power minus 1 over 2 plus k. 4 power minus 1 over 2 can be written as 1 over root 4 plus k. Minus 3 over 2 is equal to 1 over 2 plus k. When I take half on the other side, I get minus 3 over 2 minus half. This results in k is equal to minus 2. Now in part B, we need to find the equation of the curve. So we'll integrate the curve. Y comes out to be, now to integrate x power minus 1 over 2, we'll add 1 to the power. So this comes out to be x power 1 over 2 and divided by the new power. For minus 2, we'll just multiply it with x. And since we don't have the limits over here, we'll add a plus c. Y comes out to be 2 root x minus 2x plus c. We have the pair of coordinates for this curve, 4 and minus 1. So we can plug those in to find the value of c in this case. C comes out to be 3. So the equation of the curve is 2 root x minus 2x plus 3. For part C, we need to find the coordinates of the stationary point. We already have dy by dx is equal to now we know that at the stationary point the gradient is 0, so we'll equate it to 0. X power minus half is equal to 2. 1 over root x is equal to 2. And when we cross multiply, we can get so the value for x in this case comes out to be, after squaring both sides, x is equal to 1 over 4. And since the question is asking us for the coordinates, we'll also need the y value. So we'll plug in x is equal to 1 over 4 in this equation to get the y coordinate. This comes out to be 3.5. So the coordinates for stationary point are 1 over 4 and 3 whole 1 over 2. In part B, we need to determine the nature of the stationary point. For that, we'll need d2y dx squared, the second derivative. And for that, we'll need to differentiate dy dx again. So x power minus 1 over 2 is multiplied by the power itself. And we subtract 1 from the power. And the differential of minus 2 becomes 0. The second derivative comes out to be minus 1 over 2 x power minus 3 over 2. We'll plug in the stationary value of x. Now this would result in a value less than 0, since it's a negative value. So the nature would be maximum for the turning point. Moving on to question 11. The diagram shows the curve with equation x is equal to y squared plus 1 with the points a 5, 2 and b 2 minus 1, which lie on the curve. In the first part, we need to find the equation of AB. So we'll find the gradient. 2 minus minus 1 and 5 minus 2 gives us. So the gradient comes out to be 1. And then we'll use the equation y minus y1 is equal to m bracket x minus x1. We'll plug in a pair of coordinates and use the gradient to form the equation. So I'll use these coordinates, 5 and 2. Y comes out to be x minus 5 plus 2. The equation for AB is y is equal to x minus 3. So 11b, we need to find the volume between the curve and the line about the y-axis. So the first step would be, we'll change both the equations and make x the subject. X is equal to y squared plus 1 would be the curve, and x is equal to y plus 3 would be the line equation of AB. For the y-axis revolution, limits would be 2 and minus 1. So let's find the volume for the line AB first. V is equal to pi multiplied by the integral of x squared dy x squared would be y plus 3 whole squared. Now we'll integrate this. Y squared becomes y cubed upon 3 plus 6y squared upon 2 plus 9y with the limits minus 1 and 2. So the volume for the line AB is 39 pi. Now we'll find the volume for the curve. We have y squared plus 1 for the curve. When we integrate this, we'll get y power 5 upon 5 plus 2y cube upon 3 plus y. This would simplify to pi multiplied by 78 upon 5. Now to find the volume between these two, we'll need to subtract the volume by the curve from the volume by the line. The volume is equal to 39 pi minus 78 upon 5 pi, which gives us 117 over 5, which gives us 23 whole 2 upon 5 pi as the volume. This is the end of this exam.